All right, we are recording. Let's go from current slide. I'm going to try to go from current slide. There we go. And I'm going to scoot y'all over just a tad. Okay. And we'll also start from the whiteboard because the last two examples in 5.1 do not have PowerPoints. Okay. Which means I've also got to adjust the whiteboard because they make it so it blocks part of the screen. Okay, that's about the best I can do. All right, any questions, concerns, problems that you want to bring up before we get going on today's class? Anything? All right, where we left off last time was Chapter 5, Analytic Trigonometry. We're finishing up 5.1 today using fundamental identities. And we were at the top of page 352, example 8, not on the PowerPoint, so that's why we're on the whiteboard. Okay? Now, they give us a substitution to make. Here's a substitution. X equals 2 times tangent theta. Okay? And your x, the thetas here, are between 0 and pi halves. Now, okay, and what we want to do is to write that's a pretty ugly writing there. This expression, the square root of 4 plus x squared, as a trigonometric function of theta, as some function of theta. All right, now you might say, why? Okay, well, we'll get to that. Now, first, let's look at a couple of things. Number one, it's not real obvious why they chose 0 to be the lower limit, because tangent of 0 certainly is defined. Okay, in fact, you could have used tangent of anything down to minus pi halves, but they chose to end it at 0, so that's fine. This makes more sense, though. You cannot take the tangent of pi halves because that's undefined. That's that vertical asymptote. So you have to end it before you get to pi halves, and they went right up to it. This end, they could have gone further. They could have gone to negative pi halves to pi halves, as long as it's strictly less than, but they just chose to go from 0 to pi halves, which is perfectly fine. Okay? Now, what they're going to do is use this expression, this substitution, x equal 2 tangent theta, plug that in here. Okay? Well, what's the first thing you see there? You got x squared. So let's do x squared first. X squared would then be 2 squared is 4, and tangent theta squared would be tangent squared theta. So that's what your x squared would be. Now what we're going to do is add 4 to that. So 4 plus x squared would be 4 plus 4 tangent squared theta. And that's what we plug in here. So we have the square root of 4 plus 4 tangent squared theta. Okay, now that is a function of theta. But we can do a little better than that. Here we have a common factor of 4, so let's pull that out. That would be the square root of 4 times 1 plus tangent squared theta. Follow that? Okay, well, let's separate those. That would be the square root of 4 times the square root of 1 plus tangent squared theta. Well, the square root of 4 is 2. It's the principal square root, positive, and that's probably one reason they didn't do anything negative here on theta, perhaps. Okay. Now what is this? That's the square root of 1 plus tangent squared is secant squared. Well, the square root of a secant squared is secant. So there we've now written, with this substitution, this expression here becomes a function of theta here, and here comes Sharika. So let me get her marked here. All right, Sharika's here. Okay. Let me see if anyone else popped in there that I didn't notice. Yep, we should have 11 students. So let me count and make sure I've got 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got it. Okay, everybody's accounted for of the 11. Okay, we've still got several people we haven't accounted for yet. So that's what we've got. The function of theta is 2 secant theta. A lot easier to deal with than this. Okay. Now, there is a checkpoint. Please do the checkpoints as soon as you can outside of class. Now, I'm going to clear the screen. Does anyone need this a little bit longer? Okay, I'm going to clear the screen. And what they're asking us to do now is they've drawn a figure 5.1 in the margin here. It shows the right triangle illustration of the trigonometric substitution in example 8. I wish I'd have left it up here now. Okay. Here was that. I wish I'd have left it up, but it's already gone. Okay. Where is my pen? Here we go. Somewhere here. Okay, here we go. Okay. If this is a triangle, a right triangle here, okay? Now what we had there was the illustration we had was x is equal to 2 tangent theta. Okay. Now what I like to do is get the trig function by itself. So let's divide away a 2, both sides. And this gives us tangent theta is equal to 2. So if we choose this to be the angle theta, either one of the acute angles would have worked, but we're going to choose that one. Then tangent is opposite over adjacent. So that makes this the x, that the 2. So that's the triangle they're showing here. Okay. Now, with that in mind, what would be the hypotenuse? Well, 2 squared plus x squared would have to be your hypotenuse squared, right? Pythagorean theorem. So the hypotenuse would be the square root of 4 plus x squared. And that is exactly the expression we were dealing with before. Okay? Now, your secant theta, which was our answer if you remember, secant theta is hypotenuse over adjacent. So that then gave us that the secant theta was the square root of 4 plus x squared over 2. Hypotenuse over adjacent. Well, what did we have here? This expression. Let's multiply both sides of the equation by 2. And this expression here, the square root of 4 plus x squared would be 2 secant theta, which is exactly what we found our answer to be. This expression in x becomes that expression, that function of theta. So your little triangles will be very, very helpful. Okay, so hang on to them, keep up with them. Now, excuse me just a minute. Even though I had a great night's sleep, I'm just totally exhausted today. The anemia is still here. Let me get a little bit of a boost here. Hold on. Okay, hopefully that will help. All right. So our solution we got before checks out here. So let's move on to example 9. I was thinking this figure was relating to 9. It wasn't. It was relating to 8. Now, here's what we've got. Here's an expression, the log, natural log, of the absolute value of cosecant theta plus the natural log of absolute value tangent theta. Okay, it says to rewrite that as a single logarithm and simplify the results. Now, before we do anything there, let's just pause for a moment here. Why do we need the absolute value bars? Because a log, you cannot take the log of a negative number. So therefore we have to have the absolute value of cosecant and the absolute value of tangent. Now, we got a little bit more of a problem here. Cosecant, by the way, is never, ever, ever 0. Okay? It's either going to be greater than or equal to +1, less than or equal to -1. If it's less than or equal to -1, you take the absolute value. Greater than or equal to +1, then you just take the log of that cosecant. However, tangent can be 0, specifically at theta equals 0. So we have to basically exclude the possibility of theta equals 0 because you cannot take the log of 0 either. You can't take the log of a negative number, and my internet connection is unstable, so I'm going to quit talking about trigonometry for a minute. Did I break up on you some? Yes or no? Okay, sorry about that. Hopefully it's back now. So in this case, theta has to be, I'm going to say greater than or equal to, not equal to, greater than 0, but tangent is not defined for theta equal pi halves, so I'm going to say theta here has to be between 0 and pi halves. Now if theta is between 0 and pi halves, cosecant is also positive here. But it doesn't have to be that. If theta was between minus pi halves and 0, then tangent theta would be negative. You would need the absolute value bars. So they're being safe here, having both of those expressions there. Okay, now it says rewrite that as a single logarithm and simplify the results. Okay, now you have a couple of options here. One, the sum of two logs is a log of the product. That's one of the rules of logarithms. So let's write that first. The log of the product of these two. And we'll write that as cosecant theta times tangent theta. Okay, I'll keep the absolute value bars there because, again, this has to be positive. Now, what I want to do, because I don't think in terms of cosecant and tangent, I think in terms of sines and cosines much better. So let's do the log of absolute value. Cosecant is 1 over sine theta plus, and tangent is sine theta over cosine theta. Okay. when I can't think of anything else to do, I get everything in terms of sine and cosine. Okay, so let's get the least common denominator is going to be sine times cosine. So this will be the log of absolute value. And if we multiply this one by cosine, you get cosine theta over sine theta cosine theta. You multiply both numerator and denominator by cosine theta, plus this will be sine squared theta over sine theta cosine theta. Now this doesn't seem to be going anywhere. So let's see what we can do. This will be the log of absolute value. This is cosine theta plus sine theta, sine squared theta. Okay, again, that doesn't seem very helpful, over sine theta cosine theta. Okay. Maybe I'm heading the wrong direction here, but let's see what happens. Let's get this sine squared theta to be 1 minus cosine squared theta. So this will be the log of absolute value cosine theta plus 1 minus cosine squared theta, because sine squared theta is 1 minus cosine squared theta, and this will be over sine theta cosine theta. I hope I haven't made a dumb mistake here. All right, so let's rearrange this and see if we can factor that. I'm going to come over here and do that. Let's make a minus cosine squared theta plus cosine theta plus 1. Okay. Now I'm going to factor out the minus sign and make that a cosine squared theta minus cosine theta minus 1. Let's see if that will factor. Okay, that would be a minus. This will be a cosine theta times a cosine theta. Okay, and this will have to be plus and minus here. 1 and 1. That won't work. Okay, I've done something dumb here. Okay, of course I've done something dumb here. I went from a times here. Sorry about this. I'm going to have to erase a bunch. Here's what I did wrong. Sorry, my brain's not working today. We have a times here. I put a plus there. Wrong. Okay, wrong, wrong. All this is, from there on, is wrong. I knew this wasn't looking right at all. Okay, so let's start this thing over with. Sorry about that. Y'all let me get away with that. What were you doing, huh? You were supposed to be catching my dumb mistakes. So let's get rid of all this. I was thinking this is not going anywhere fast. Okay, I don't know how in the world I did that. Change that times to a plus. Wrong answer. Okay. All right. This is a times here. Well, with the multiplication there, which is what we had here, this is the signs here divide out, and you're left with 1 over cosine theta. Isn't this so much easier? This then is the log of 1 over cosine is secant theta. And I think that has us right where we need to be as a single logarithm, and simplify the result. There it is. We don't even need this down here at all. That's the log of absolute value secant theta. I think that's as simple as we need to go. Yep, that's it. Log of absolute value secant theta. Sorry, we started down the wrong rabbit hole. Okay, there is a checkpoint. Please do the checkpoints. Okay, now we're ready for 5.1 exercises. Okay, vocabulary, top of page 353. 6 questions here. Fill in the blank to complete the trig identity. What is sine u over cosine u? Anybody? Tangent u, perfect. What's 1 over sine u? We just used it here. 1 over sine u was cosecant u. What's 1 over tangent u? Cotangent u, perfect. What is secant of pi halves minus u? That's the secant of the complement of u would be the cosecant of u. That's what the co stands for, complement. Okay? What's sine squared u plus cosine squared u? Please get that one right. 1, perfect. And what is sine of negative u? Sine is an odd function. So what would sine of negative u be? Negative the sine of u. Odd functions, they'd be going in opposite direction. Okay? Now, that was the vocabulary. Here are your skills and applications. Do any of the odds 7 through 11. They're all at Calc Chat. 7's at Calc View. 13 to 17, all at Calc Chat. Actually, I think I would do all those, okay, because it's just matching. The answers, though, are only for the odd problems. Do either 19 or 21. Both are at Calc Chat. 19's at Calc View. Any of the odds 23 to 31. They're all at Calc Chat. 25's at Calc View. 33 to 39, all at Calc Chat. 35's at Calc View. Do 41 is a Calc Chat. Any of the odds 43 to 47, they're all at Calc Chat. 43's at Calc View. 49's at Calc Chat. 51's at Calc Chat. Either 53 or 55 are at Calc Chat, with 53 being at Calc View. 57's at Calc Chat. 59's at Calc Chat. Either 61 or 63, both at Calc Chat. 61's at Calc View. 65's at Calc Chat. Should be anyway. 67 should be at Calc Chat. 69 should be at Calc Chat. And then any of the odds 71 to 75, they should all be at Calc Chat. Okay. So 5.1 dealt with your fundamental identities. Playing around with them, getting used to them, get to know them, get familiar with them, know what they are, what they stand for. Because in 5.2, which is what we're going to now, here we go here, and we'll go from current slide, we are going to be verifying trigonometric identities. Big, sort of more complicated, but we're going to use those fundamental identities to help us do that. Okay, so our objective here is to verify the trigonometric identities. Now, a little bit of background here, introduction. Okay, in this section you'll study techniques for verifying trigonometric identities. What do we mean by trigonometric identity? Okay, when you have an expression, any expression that has an equal sign in it, that means it's an equation. Now there's two types of equations. One is what they call a conditional equation. That's an equation that's true for only some of the values in the domain. So for instance, sine of x is equal to 0. That's an equation. That's not true for every x. It's only true for your multiples of pi. Sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, sine of negative pi is 0, not sine of negative 2 pi is 0. Only for your n pi's is that equation true. That's called a conditional equation. It determines which values of x you have. Okay? Now this n here is an integer, any integer, positive or negative, but an integer. Okay? When you are finding the values that make that true, you're solving the equation. Okay? That's a conditional equation. What we're doing in this section, and for a lot of this chapter, we're going to be finding equations that's true for all real values in the domain. That's called an identity. For instance, this is 1. Sine squared x is equal to 1 minus cosine squared x. Why is that an identity? If you added cosine squared x to both sides, you have sine squared x plus cosine squared x equal 1. That's always true. No condition to it. It's always true no matter what value x you put in there. Every real number x, that's an identity. So in this section, we're going to be verifying identities, not solving equations. They look a lot alike, but they're not. These are going to be identities, and we're going to need to verify and make sure they're true. Okay, that's where we're starting from. So the first subtopic here is verifying trigonometric identities. And here comes Courtney. Good deal. So let me get Courtney marked here. Perfect. The bottom part of the alphabet is here very, very strong. It looks like the bottom 1, 2, 3, 4, 5, 6, 7, 8 people are here. Top part of the alphabet, we only got 4 out of 5. Okay, so hopefully the rest of the alphabet will show up. Okay, so we're going to, Courtney, by the way, we're in Chapter 5, Analytic Trigonometry. We're in 5.2, just got here, verifying trigonometric identities. Okay, and we just went over what an identity is. That's an expression that is always, always true. We have equations that may be true for only certain values, but an identity is always true for all values. And we're going to be verifying those. If I could get the slide to advance here. Here we go. Although there are similarities, verifying that a trigonometric equation is an identity is quite different from solving an equation. There's no well-defined set of rules to follow to verify trigonometric identities. It's best to learn the process by practicing. Now here are some things I try to keep in mind. When you're solving an equation, you're always trying to simplify and get down to your variable. That's not what we do when we're verifying an identity. Okay? Now, what we do when we're verifying identities, okay, is basically, now here's the deal. When you're solving an equation, you usually move everything not your variable onto the other side. Okay? That's how you solve the equation. When you're verifying an identity, you never cross the equal sign. Never. Do not cross the equal sign. Simplify one side, simplify the other side, but never cross the equal sign. When you're solving an equation, you're always crossing the equal sign. In verifying identity, do not cross the equal sign. Okay? So, what they suggest is sort of what I was just saying. Work with one side of the equation at the time. I don't think that's absolutely necessary. Just don't cross the equal sign. That's why they're saying work only with one side at a time, so you don't cross it. But as long as you keep in mind you can't cross the equal sign, you can do both sides at the same time. Just don't cross. It is often better to work with the more complicated side first. That's usually a pretty good idea. You don't have to though. Okay. Number 2, look for opportunities to factor an expression, add fractions, square a binomial. Now be careful with that one, okay? Or create a monomial denominator. Usually a good idea there, okay? A lot of the things we did in section 5.1 will be repeating, okay? Look for opportunities to use your fundamental identities. I would list that almost number 1 here. Note when the functions are in final expression. Note which functions are in the final expression you want to get to. Sines and cosines pair up really nicely. Secants and tangents pair up very nicely. Cosecants and cotangents pair up very nicely, especially if they're squared, because sine squared plus cosine squared is 1. Tangent squared plus 1 is secant squared. Cosecant squared is equal to 1 plus cotangent squared. That's why they pair up nicely. Anytime they're squared, try to fit in your Pythagorean identities. If the preceding guidelines do not help, then try converting all the terms to sines and cosines. Now sometimes I'll do that very early in the game. I don't wait until step 4. Always try something. Even when you're going down a rabbit hole and not getting anywhere, a dead end, you might get insights. Oh, but I could try this. Okay, so always try something. Okay, those are general guidelines. I don't necessarily like the order of them, but we'll see what works. Okay, so verifying trigonometric identities is a useful process when you need to convert one trigonometric expression into a form that's more useful algebraically. That's why we do this. When you verify an identity, you cannot assume that the two sides of the equations are equal. That's what you're trying to verify. So most of the time I'll put a question mark over that equal sign just to make sure we don't assume that's true. As a result, when you're verifying identities, you cannot use operations such as adding the same quantity to each side, cross multiplication. You cannot cross the equal sign. Keep that in mind. So the steps you use for solving equations, do not use those when you're verifying identities. Stay on one side or the other, but don't cross the equal sign. So here's the first one. Okay, let me get my pad and pen here. Try to verify this identity. Okay, now here's the things I note. You have a bunch of squares here. Okay, that leads me to say let's think in terms of Pythagorean identities. If you didn't have any squares there, not a good idea. But when you have the squares there, think in terms of Pythagorean identities. Okay? Now, let's think, what in the world is secant squared minus 1? Well, let's go back to our fundamental Pythagorean identity. That was simply sine squared theta plus cosine squared theta is equal to 1. Okay? Now, how do we get a secant square out of that? Well, secant squared is 1 over cosine squared. So let's divide everything here by cosine squared. You don't have to go back this far if you don't want to, but I like to do it this way because this helps me remember what we're dealing with, and divide that by cosine squared theta. Okay, now let's fill in what we got. This is a tangent squared theta, right? Sine squared over cosine is tangent squared. Cosine squared over cosine squared is just simply 1, and 1 over cosine squared is our good old secant squared theta. Okay, so let's subtract the 1 from both sides. And that gives us tangent squared theta is equal to secant squared theta minus 1. That's exactly what we've got here. So let's put that in its place. That would be tangent squared theta over secant squared theta. And that is supposedly, and this again, I usually put the question mark here, supposed to be equal to sine squared theta. We don't know that it is. That's what we're trying to show. Well, now let's get what is tangent squared theta. Tangent squared theta is sine squared theta, just like we had up here, over cosine squared theta. Over secant squared theta is 1 over cosine squared theta. Okay, the question is that equal to sine squared theta? We don't know, but we're going to see. Well, what we have to do here is multiply by your denominator, cosine squared theta, and multiply down here by your denominator, cosine squared theta. Now, why do we do that? Cosine squared theta over cosine squared theta is 1. But if you leave it there, you see that wipes out that one, that wipes out that one, and what do you have? Sine squared theta is equal to sine squared theta. That indeed is equal to 1. I mean, they're equal to each other. We've just verified that identity. Okay? Now, any question on that before I erase it? Okay, let's see if they did the same thing in the book. Start with the left-hand side because it's more complicated. Well, it's also not in terms of sines and cosines. I like that. Okay, I like to get them. Okay, so this is secant squared theta over minus 1 over secant squared theta. Now, boy, did they go around the elbow to get to the ear. This is simply tangent squared theta. Okay, we showed that, but they rewrote secant squared theta as tangent squared theta plus 1, then minus 1, and that's just tangent squared theta over secant squared theta. I thought, they did a little extra work there. Okay, so this gives us exactly what we got, tangent squared theta over secant squared theta. Now get in terms of sines and oops, okay, really bizarre. I would have gone straight to sines and cosines here. This is sine squared over cosine squared divided by 1 over cosine squared, which they sort of did here, okay, and sine squared theta over cosine squared theta times cosine squared theta. That gives you sine squared theta, which is exactly the right-hand side. So they got there the same way, well, slightly different steps, using the same identities that we used. They just did them in a weird fashion. As long as all the steps you're doing are correct, you should come out fine. Okay? I am still very anemic, so I'm going to try to get a little more caffeine and sugar to boost my energy level. Hold on just a minute. Unfortunately, I didn't bring a lot up here, so we'll see if I can make it. All right. That's equal to sine squared theta. Right-hand side of sine squared theta, left-hand side of sine squared theta. Notice that you verify the identity by starting with the left side. That's what they choose, the more complicated side, using your fundamental trig identities to simplify that until you get to the other side. Okay? You don't have to do it that way. We'll see other examples where you don't have to, but this was the way to go on this problem. Any questions? Okay, there was example 1. That was at the top of page 356. There is a checkpoint. Please do the checkpoints as soon as you can after class. Okay. Now, they do make a little statement here. Let's see if they put it on the... Oh, my goodness, look at that. They end the slideshow after what? 2 or 3 slides, and that's all. Now, we're going to continue, but we're going to continue via the whiteboard. Okay. And okay to clear this one. Okay. They make a statement here, just like we've shown, there can be more than one way to verify an identity. And they show another way of doing it. As long as all your steps are correct, you should get the same results. Okay, now let's move on to example 2. Not on the PowerPoint, okay? So let's do this one. Verify this identity. 2 times secant squared alpha is equal to, or supposedly, this is what we're trying to show, 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. Yuck. Okay, sorry about that. This board that I use, the Wacom board, has these buttons, and anytime my hand hits a button, it does weird things. Okay, now, kind of hard to decide who is the, which is the easy, which is the harder side. Sure, the right-hand side looks a little more complicated. But you know what? I want to mess with this side too. I like to get things in terms of sines and cosines if I can. So this will be 2 over, because secant squared theta is 1 over cosine squared theta. So let's put this as cosine squared. I'm sorry, I said theta, it was alpha. So this is that. Is that the same as the right-hand side? Well, it's not very obvious. Well, here you have sum of 2 fractional forms. Well, how's the only way you can do that? If you have least common denominators. What are the least common denominators? The product of the 2. Okay, so we're going to do that. We're going to get the product of these 2 common denominators is 1 minus cosine alpha times 1 plus sine alpha. Okay, so this denominator is going to be 1 minus sine alpha times 1 plus sine alpha. Okay, but what did we do? We just multiplied the denominator by 1 plus. That means we have to multiply the numerator by 1 plus sine alpha. Okay, plus, now this denominator was already 1 plus sine alpha. For some reason, this pen just refuses to write reasonably. We want to multiply that by 1 minus sine alpha to get least common denominator. 1 minus sine alpha, but that's a minus there. We multiply the numerator by 1 minus sine alpha. Okay, these two have to be the same, those two are the same. All right, so what do we have? 2 over cosine squared alpha, not much that we had to do there, done. Is that equal to, now, we have least common denominator, so we can add the numerators together, okay, keeping the denominator. Well, let's multiply those 2 denominators together. A lot of times I don't want to do that. This time I do. This is 1 minus sine alpha times 1 plus sine alpha. 1 plus sine alpha times 1 minus sine alpha. That adds to 1 minus sine squared alpha. Whenever you multiply the conjugates together, you get the difference of their squares. You know that, okay? Well, let's add the numerators now. Here you have a 1 plus 1, that would be 2. Here you have a plus sine alpha plus a minus sine alpha. Those add to 0. Uh-oh, look at this. This is 2 over cosine squared alpha. That's what we had here. Over here we have 2 over, well, what's 1 minus sine squared? Pythagorean identity, cosine squared. So sure enough, no more question mark, that is an identity. Those are identically the same. So therefore we verified that this thing here is indeed equal to that thing there. They don't look like they would be at all related, and yet they are exactly the same. So that's your example 2. They left it in terms of 2 times secant squared theta or alpha. It doesn't matter. As long as you get the same results, you got it. Any questions on example 2? These get to be pretty much fun. They're sort of like a puzzle. Now, I've always loved puzzles, so this makes it pretty much fun. So let's go, unless there's questions on example 2, let's clear our screen so we can do example 3. Any questions? No? All right. Let's do example 3. Verify this identity. Here we have a tangent squared x, you can use any variable you want to there, plus 1, and they're multiplying that by cosine squared x minus 1. And the question is that equal to a minus tangent squared x? Okay. Now this is probably one that you have multiple ways of solving. Okay. Most of these you have multiple ways of solving. Okay. Now, when I see the squares there, I think Pythagorean identities. And sure enough, this is exactly, we did it before, secant squared x. 1 plus tangent squared x is secant squared x. So let's just write that down, make that a little simpler. Okay? Now, this one looks pretty familiar, but it's not quite right. Cosine squared x minus 1, that's not a Pythagorean identity per se. 1 minus cosine squared x would be. That would be sine squared x. Well, guess what? Since these are reversed, that would be minus sine squared x. Okay? Because that's the opposite of 1 minus cosine squared x. Okay? Now the question is that equal to minus tangent squared x? Well, you know what I want to do? I want to get this in terms of sines and cosines. So let's write that as minus sine squared x over cosine squared x. Okay? Now, let's get this one in terms of sines and cosine. This is 1 over cosine squared x, your reciprocal identity. Secant squared is 1 over cosine squared, times a negative of the sine squared x. And guess what? That is indeed equal to minus sine squared x over cosine squared x. My pen's not writing very well because this is minus sine over cosine. This is minus sine over cosine. Done, done, done. Okay? Now, you didn't have to work with both sides independently. You could have carried that through and just seen this is indeed minus tangent squared x. Okay? But it might have taken an extra step. Why not do both sides at the same time? Just do not cross the equal sign. Do not cross the equal sign. Okay, I'm getting very dry again. Hold on. Okay, that was example 3. Let's do example 4. Now this may take a little bit longer because it has multiple parts to it. Any questions before I clear that screen? for example 3. By the way, I don't say this every time, but let me make sure I say it. Every example usually has a checkpoint. So please, folks, do the checkpoints. So let's go to, if no one need me to leave this longer, let's clear this out of the way. All right. Example 4. There are 2 here we're going to do. The first one is this one. Tangent x times cosecant x is that equal to secant x? Now, the earlier ones had a bunch of squares in them. That usually led to Pythagorean identities. This one doesn't have a square in it anywhere that's visible, so I wouldn't even mess with Pythagorean identities. So let's get, and this is the place where I say, get everything in terms of sines and cosines. What is tangent in terms of sine and cosine? Well, that's sine x. This is your quotient identity or ratio identity over cosine x. Okay? What is cosecant x in terms of sines and cosines? That's your reciprocal identity, 1 over cosine x. Okay? Now, let's do the right-hand side. What is this? Secant x is 1 over cosine x. I'm sorry. Y'all let me do that? Now my pen will not go to erase. Cosecant is 1 over sine. I can't use my eraser, so let me just write this as sine x. Can't believe you did that. Okay? And this is 1 over cosine x. Okay? Well, look at what happens. This sine x cancels that sine x or divides it away, and you get 1 over cosines equal to 1 over cosine. No more question there. That's exactly the same. So that was pretty straightforward. Fairly easy. Let's do the B part. The B part here says that tangent x plus cotangent x supposedly is equal to secant x times cosecant x. Okay, again, I can't use my eraser here. I don't know why. Sometimes it works and sometimes it doesn't, but it will not open now, so I can't erase. Again, no Pythagorean identities, no squares in here. Maybe you could make that happen, but get everything in terms of sines and cosine. Tangent x is sine x over cosine x. That's your quotient identity or ratio identity. Plus, now cotangent x is cosine x over sine x. It's just the reciprocal of your tangent. So this one's just reciprocal of that one. Now the question is that equal to? Well, let's do the same thing here. This is 1 over reciprocal identity, 1 over cosine x. Get to know those identities, folks. They're going to help you out big time. Cosecant x is 1 over sine x. Okay. Now, here we have a sum of 2 fractional forms. You need to have least common denominator. So we'll multiply this one by sine x, multiply numerator and denominator by that. This one will multiply numerator and denominator by cosine x. So this will give you sine squared x over sine x cosine x, right? Just multiply numerator and denominator by sine x, and you got that. Plus, to get the same denominator here, sine x cosine x. What you had to do was multiply the denominator by cosine x, so you multiply the numerator by cosine x as well. That gives you cosine squared x. Okay? Now the question is that the same as this? Well, this is a multiplication. All you do is multiply the numerator together, 1, multiply the denominator together, sine x times cosine x. This is beginning to look like it might be helpful, because now you have same denominators here. You can just keep the denominator, sine x cosine x, okay, and add your numerators together, sine squared x plus cosine squared x. And guess what, folks? Is that the same as 1 over sine x times cosine x? Sure it is, because sine squared x plus cosine squared x is equal to 1. So you get 1 over sine x cosine x on this side. My pen is not writing well at all. And that is indeed equal to 1 over sine x times cosine x. Those are exactly the same on both sides. We have verified that identity as well. So, once you do these, do enough of them, try different things, see what works. Usually if you have a bunch of squareds, try Pythagorean identities. If you don't have any squares, try getting them into sines and cosines. Fiddle around with them until you see if something will work. Okay? Now, they come up with a different identity at the bottom, but they're the same identities, okay? So, as long as that works. There is a checkpoint after example 4. Please do the checkpoints. All right, any questions on example 4? All right, now, on page 358, we were just on 357. On 358, there is a thing at the top of the page that's called, they remind you of rationalizing a denominator, which is an okay concept, and I think it works pretty nicely, but I like to think of it in a different way. Okay? Whenever you have a form like this, 1 over 1 minus cosine x. Okay? Now they call it rationalizing the denominator. I call it multiplying by the conjugate. Okay? So why would you do this? Well, number one, this is a difficult thing to do because you have a monomial in the numerator, a binomial in the denominator. There's not really an easy way to simplify that. But if you multiply by the conjugate, which is 1 plus cosine x, of course, if you multiply the denominator by that, you must multiply the numerator by that as well, 1 plus cosine x. Why? Because 1 plus cosine x over 1 plus cosine x is 1. Okay? Same thing. Numerator over denominator is 1, so you haven't changed the value in it, just the way it looks. Now that probably looks more complicated to you. But what do we have here? When you multiply 1 times that, you just get that. 1 plus cosine x. But when you multiply the conjugates together, that's the sum times the difference of the same two entities. That's the difference of their squares, which would be 1 minus cosine squared x. Okay? Well, guess what that is? Good old Pythagorean identity. That is sine squared x. So what we have here is 1 plus cosine x over sine squared x. Now, that doesn't look a lot easier, but guess what? Okay, you can express this. This isn't the only thing you can do, but you could. Because you have a binomial in the numerator and a monomial in the denominator, this could be written as 1 over sine squared x, and this is plus cosine x over sine squared x. You just undo your addition of your numerators. This could be expressed as secant squared cosecant squared x, I almost did it again, reciprocal identity, plus, and this is cosine over sine, and this is 1 over sine. Okay, what does that give you? Cosecant squared x plus, this is cotangent x, and this is cosecant x. That's a lot simpler than, well, you lost your denominator. That's the key. Anytime you can lose denominators, usually a pretty good idea. Okay? Now, you could have also, at this point, and this is just playing around, factor out a cosecant x, and that would have left a cosecant x plus cotangent x. There's another identity. Okay? Again, nothing special about these, but it just shows you can take something that was in a fractional form here, if I could get my pen to show up, that started out being a fractional form, and you got it into something that contains no denominators at all. Okay? And some people don't like denominators. Okay? I don't particularly care for them myself either. Okay? Now, the reason they say this form here is a little preferable to this one doesn't contain denominators, that one does. And it's fairly complicated. So let's move on to example 5. Any questions on what we were just doing there? Let's go to example 5. All right. I'm going to need something else to drink. Sorry about this. Not much sugar and caffeine there. All right. Only about 6 minutes. I think I can make it. Let's see if we can get example 5 done in 6 minutes. Now, example 5, even though it's not on the PowerPoint slide, you can go to larsonprecalculus.com and see an interactive version of that type of example. So here's what we're trying to verify. Secant x plus tangent x supposedly they're saying this is equal to cosine x over 1 minus sine x. Okay. Now again, I'm probably going to follow a slightly different bent from what the book does, but remember, if all your steps are correct, you should still get the same verification. Now, here's the deal. This side doesn't have any denominators, so that's sort of simpler. This one does have denominators, but it's in terms of sines and cosines. So it's kind of a toss-up, which is more complicated. So you know what I'm going to do? I'm going to get this side in terms of sines and cosines, also try to get rid of your denominator here. So this becomes 1 over cosine x. That's what secant is, reciprocal identity, plus this is sine x over cosine x, your ratio identity or quotient identity. Okay, so we'll leave that alone for a moment here and go to this side. Well, this side we have one of those conjugates down here, so let's multiply it through by 1 plus sine x. Okay, but if you multiply the denominator by that, you must also multiply the numerator by that. 1 plus sine x. The pen is not writing well at all. Okay, so what do we have over here? You have least common denominator, cosine x, so just add your numerator together. 1 plus sine x over cosine x. Okay, on this side, we have, now I suggest leaving that in factored form for now. This will be cosine x times 1 plus sine x. Leave that numerator factored. And down here we've got 1 minus sine squared x. 1 minus sine squared x. When you multiply a number by its conjugate, an expression by its conjugate, you get the difference of the squares. 1 minus sine squared x. That's why we did it. Well, what is this? Okay, this one is pretty much fixed now, so let's leave that alone for now. But this becomes 1 minus sine squared x is cosine squared x. Pythagorean identity. Up here we have a cosine x times a 1 plus sine x. I think you see maybe now why I said don't multiply it through, do this. This cosine cancels one of those out, so you're left with 1 plus sine x over cosine x, and that's exactly what you get on both sides, so that is verified, that identity. Now they go through a few more gyrations to get there, but they come out with basically verifying they are the same. Whatever you get, just don't cross the equal sign, but simplify one side, simplify the other side. If you ever get the same form on both sides, you've got it knocked. Okay? So there was example 5. There is a checkpoint after that. Please do the checkpoints. Now that gets us down to 11:14. I don't think we're going to get example 6 done in 1 minute. So let me get my pen here, my pencil here, I mean, and let me erase where I left off last time, and we'll pick up next time with example 6. Okay, we almost finished the section. Okay, so we'll begin next time on page 359, example 6, top of the page. We'll do example 6 and example 7. Example 7 has 2 parts, and that finishes 5.2. We'll finish 5.2. Now, homework exercises here would be do either or any of the odds 3 through 7. They're all at I'm sorry. Those are your vocabulary. Any of the odds 9 through 17. They're all at Calc Chat. 9's at Calc View. Do any of the odds 19 through 23. They're all at Calc Chat. 21's at Calc View. Do any of the odds 25 to 29. They're all at Calc Chat. 27's at Calc View. Do any of the odds 31 to 35. They're all at Calc Chat. 33's at Calc View. Then do any of the odds 37 to 41. They should all be at Calc Chat. You can try doing 43. I don't really care for it too much. It's something that is not true, okay, and you're trying to find where they made the error. So they put big red X's there. I don't like them to print something that's not true, okay. You can try to do, let's see, yeah, try to do some of the odds 47 to 49. They should all be at Calc Chat. and 51 or 53, they should be at Calc Chat. 51 should be at Calc View. 55 should be at Calc Chat, and either 57 or 59 should be at Calc Chat. 57 should also be at Calc View. We'll hold off on the rest of those until we finish the last two examples. Any questions? All right. Whenever you finish it, okay? Try to have it done before we get to test 3, okay? Test 3, we're only in 5.2, almost in 5.3. We're going through 5.5, so you've still got a couple of weeks, I would say. But please get it done as soon as you can, and we'll go from there. Now, a question came up in my first class, and let me address it here too. The question was, are we having class on Tuesday? Tuesday is one of the most important days that we've had in a long time. It is election day, okay? And I want all of you to vote. If you're registered to vote, please vote. If you haven't already voted, please vote. Now, do you have time to vote except for during this class? If you do, please vote sometime. The polls are open from 7 till 7. However, if you don't have any other time except this class, I would rather you vote and then watch the YouTube videos, because I will be recording, just like I'm recording this time. I will be recording next time as well, as everything works, okay? So, but if you can be here, if you can't possibly be here and vote, vote first and then try to get here. If you can't get here, watch the YouTube video, because I will be, knock on wood, trying to record it, and so you would have it. Even if I can't record it, I'll leave it out there from the last time, so you should be able to follow whatever we do in class. We will hold class, but I want you to vote if you are registered to vote, and I hope you are. Now, some of you may not be able to vote because maybe you're not U.S. citizens, you may be an international student or something like that. If that's the case, understand, okay? Hopefully you'll be here then. But if you can vote, please vote. Good deal. Any questions? All right. Did that answer your question about the test, test 2?
Yes, sir.
All right, good deal. All right, then we will see you. Be careful this weekend. The rates are still skyrocketing now. Even though it looks like it might be a pretty nice weekend, be careful, be safe, and take care. Now, I forgot to tell my first class, we're supposed to leave town tomorrow, so I may not be available until late Monday. We'll be back in town, but I've got class from 10 o'clock until 4 o'clock. So if you're trying to get in touch with me over the weekend, we're going to be in places that have really lousy internet service. So anyway, if you can't get me, don't get frustrated. I'll try to get caught up when I get back on Monday. Okay? Any questions? Yes? Test 2 covered from 4.5 to 4.8. Test 1 was 4.1 to 4.4. Test 2 was 4.5 to 4.8. Test, right. And the next test will be all of Chapter 5, 5.1 to 5.5. And then the last test will be all of Chapter 6 that we cover. We may not be able to cover it all, but yeah, that'll be how it goes. All right, good questions. Any others? All right, well then I'm going to end the meeting for everybody, telling you again, be safe, be careful, don't get exposed, okay? Try to be as safe as possible. Take care, folks. We'll see you on Tuesday, hopefully. Please vote if you can. Bye-bye.